All right. Well, thanks for coming, everybody, to week 7 of Introduction to Astronomy Research 2021. We have an exciting agenda for you today. We have a special guest lecture from Vishal Gajjar from Breakthrough Listen. We'll be talking a little bit about the final projects that will be due at the end of next week and how we're going to help you prepare for that, both online and for in-person meetings. Your final projects will be one of the best ways that you'll have to engage with the mentors on the call here. So please stay tuned for details about that. And then after that, we'll have a discussion of the direct imaging of exoplanets paper. So stay tuned for all of that. And without further ado, I'd like to introduce Vishal Gajjar. Take it away, Vishal.
Thank you, Howard. Thank you for this opportunity to speak to you all. Let me share my screen. All good?
Looks good.
All right. So hello, everyone. My name is Vishal. I am a project scientist at the Astronomy department at UC Berkeley. I work with Howard and others to basically look for extraterrestrial intelligence. So in today's presentation, I'll try to kind of give you a brief outline of what activities that's happening and basically try to just give you a broad overview of what exactly we do in SETI. Obviously, I will not have time to go into much of the details, but please feel free to kind of reach out to me or Howard if you have any question regarding anything that I'm talking about today. So if you look at the sky at night, what do we see? We see like lots of numbers of stars. We ask ourselves, are there any sort of stars which have Earth-like planet around it? You have heard talks about extrasolar planets. This is an interesting question, but it actually leads to an even more interesting question, is that are we alone in the universe? Is there any life out there? And that's something that's kind of keeping us busy for at least last several sort of, I would say, decades. There has been a very new recent development which has kind of allowed us to think this in a little bit more of a positive sense, because we found out that the Earth is not a unique planet, because we found at least something around more than 5,000 extrasolar planets already, out of which so many of them are typically type of that we have seen on Earth. So they are actually in a what we call in a Goldilocks zone, which is kind of not so far from their star and not too close from their star, and exist in the right spot where liquid water could exist. And if liquid water could exist, maybe those systems will have life on it. So we have already found out about these systems. So basically, what we know right now is that if you look at the sky at night, you don't just see stars, but almost all of these stars likely to have planets around it. Now, that's a great news for us. Like if you're really interested in this question, if we are alone in the universe, having so many planets actually is a good thing, right? So we ask this thing, like if planets are so common, is life common? And then that also kind of, we see a promising evidence on our Earth itself. We see existence of life in extreme environment that we don't expect to find. These are called extremophiles, but they do exist. Like for example, at the bottom of the ocean where no sunlight actually reaches there, and there is an entire ecosystem of life which actually survives on the heat generated by our own Earth. So it is not necessary for these planets to exist in a right suitable condition that we actually have on Earth. Life could exist in other places as well. So if you talk about if the life could exist in just such extreme environment, it would definitely going to evolve as well. To kind of quote a famous thing, like life finds a way from Jurassic Park, which is true. Like life, once it gets started, it naturally evolves and adapts to its environment, and it evolves to an evolutionary. It evolves to a state where we call an intelligent life. So we already have some tools available at our disposal, which will become available in a couple of, maybe within a few years, which allow us to really look for biological life, or what we call biosignature, by which we will be able to look at the atmosphere of many of these exoplanets that we have found. So if we are able to detect some of these molecules that we all know that only life could produce, from these on these exoplanets, that would be a very good indication that maybe those systems will have life on it, because there are no other natural ways for these molecules to exist in the atmosphere of these exoplanets. So there have to be some kind of a biological processes might be giving rise to them. And this is what we call biosignature. So my speculation is that we would find such kind of life within the next few decades. That shouldn't be hard. But the main question is about intelligent life. Intelligent life, is it common? Let's say, even if you find life, it won't be, there will be ambiguity in it, because there are other abiotic processes which could give rise to such molecules as well. But intelligent life would be something that we would be able to kind of confirm it with much more certainty than biological life. We would be able to confirm biological life if we actually go and sample it, but we won't have that possibility within the next maybe several thousands of years. But intelligent life is something that we would be able to detect, and we'll be able to confirm that that is a true evidence of we are not being alone in the universe. So now the question is, how can we find the intelligent life? There are various ways by one can look at it. I'm sure you have heard about talks on how people find planets. So typically when planet passes in front of the star, a small fraction of star's light actually dips, and that's how you basically find a planet. There was a very interesting planet called the Boyajian star, which was recently, maybe a couple of years ago, was found, which seemed to show unusual dips pattern. And people speculated that because, first of all, if there is a planet going around in orbit, you should expect to see these dips in a very periodic fashion, and they should have exactly similar kind of light being absorbed almost every time. But they didn't see it. So these dips were quite unusual. And in some instances, they absorb something like 5% of the total radiation from the star, which was quite a lot. So people speculated maybe it's some kind of an intelligent life out there in the star, which has basically built some kind of what we call a Dyson sphere. So we could kind of hypothesize that we are currently on Earth. If we keep our technological advancement in a right path, we will be able to reach at some level where we will be able to harness the entire energy of our planet, and we will be able to advance to a state which we call Kardashev type 2 civilization, by which we can harness the energy output of our entire sun. By which what we mean is that if you build an enclosure around the sun, you will be able to capture all the energy output of the sun and use that for our own application. These are the hypothetical idea called Dyson sphere. So if there are such Dyson sphere out there, you would expect to find light from that being obscured by a large fraction. So maybe it was something like that. But it turned out that there are some natural explanations. For example, like gas around the stars could also do that. So obviously we didn't find intelligent life. So how else we will find? Like, for example, we can find, we have launched some of these spacecraft, which are actually exploring our own solar system to understand the origin and properties of planet within our solar system. But they don't really just do that. They also travel across, they are likely to travel across interstellar distances. So if there are intelligent civilization out there, if they capture any of these probes, they would know this is not a natural body. This has to be produced by some kind of some intelligent being must have produced them. If we could ask this question other way around, if you find something similar in our solar system, maybe that way we'll be able to find intelligent life. But that finding such thing is way hard. It's not going to be easy. So what are the other ways? So we think about other ways. There are various ways by which communication or information can travel across the universe. And one of the best ways we found out is the electromagnetic waves. So light is electromagnetic waves. Similarly, radio waves are also electromagnetic waves. The advantage of radio waves is that stars typically don't emit a lot of radio waves itself. So let's say you have a planet around a star, and that planet is actually emitting radio waves. That radio waves would be bright enough for anybody to detect across large distances, because the sun itself or the star itself is not producing a lot of radio waves. While if you emit light, you have to produce a lot of light in order to really, put your head above the water, because the sun itself or the star itself produces a lot of light. So that is one of the reasons why we think that if there are other intelligent civilizations out there, a best possible way to find them would be to look at radio frequencies. There are also other advantages. We could do this by sitting on the ground because the radio waves can easily penetrate our atmosphere. That's not typically true for our entire electromagnetic spectrum. The electromagnetic spectrum goes from radio waves to all the way high up to gamma rays. Most of the light, most of these electromagnetic waves higher than light doesn't really penetrate the Earth atmosphere because they get absorbed. So if you want to study the universe at these frequencies, you need to go to space. You need to build satellites. You need to build telescopes which operate at these frequencies, and you need to go in space. But you can do radio astronomy quite easily sitting on the ground because most of the radio waves that we are interested in actually can easily come to us. So we have this very natural window to look at the universe, and we want to basically search the radio spectrum to look for life. So how do we do that? We are all carrying a radio antenna in your pocket. So a simple mobile phone is a radio antenna. A radio antenna can also be called a radio telescope if you are able to direct the signal that is received from an antenna in one particular direction. Like an optical telescope that you might have all seen, in which you see through it with a primary mirror and a secondary mirror, and then you will be able to see objects. Similarly, in radio waves, you are also able to study objects which are emitting radio waves. You all have seen a radio dish. Typically, radio waves, when they come, they get reflected off the dish and they get focused in one place. And there are lots of electronics which convert these radio waves into electronics, and that we can feed into computers to process it. So we will be able to basically visually, we don't really see radio waves by our eyes, but by using radio telescope, we would be able to see, we are already seeing the radio waves coming from the sky. Right? We are able to understand where they are coming from and be able to understand what are the different sources which give rise to them. The advantage of using radio wave is that the radio waves can travel a lot of distance without being obscured by the intervening medium. For example, if you look at the bottom left plot, you can see that on Earth, if you transmit a bright radio waves, you can transmit this radio wave all the way to the other end of the galaxy. So radio waves are way powerful than anything else that we have yet to encounter. So what are the different types of radio waves, and what are the type of signal we are searching for? So there are various different classes of signal we call that typically we try to search for in this field. One is called deliberate transmission. Now, you ask this question, if there are intelligent civilization out there, they might be using radio for their own technology. They know the advantage of radio. So they might choose to transmit a deliberate signal at radio frequencies. And for that, we could use a radio existing antennas to capture it. So what I'm showing you right now is a telescope called Arecibo. Unfortunately, that telescope is no longer operational because it got destroyed due to some mechanical failure. That telescope was in Puerto Rico, but it used to be one of the largest single dish telescope at that point. Right now, that label goes to the FAST telescope in China, which is slightly bigger in size. But what I'm trying to kind of convey is that if you transmit a signal from a telescope like we already possess, such signals can actually travel all the way to other end of the galaxy. So we already have the technology. We don't need to build anything extra. So we are already that level in our sort of technological advanced stage that we can produce signal which can easily travel to the other end of the galaxy. So it doesn't require a lot of other resources. So we already have that. We could cast this question that the ET or the other extraterrestrial civilization might also possess such a similar advantage, so such similar advances, and they will also be able to produce deliberate radio signal. The other classes of radio signal, which we call the leakage radio signal. So we use radio to communicate, and we use radio for our own application. So we have radio waves, which are, for example, if you come to Bay Area, you might have noticed the Sutro Tower right on top of the hill in San Francisco. That is a radio antenna. If you visited an airport, you might have seen a big dish, or there are some rotating dishes that you might have seen. Those are the radars for aircraft. There are also more powerful radars, like, for example, NASA uses to detect asteroid in the solar system. Those are called planetary radars. And those are pretty powerful signals. Although we won't be able to detect signals such as like the one you have here, they can only be detected up to a few light years. But signals like this, for example, that we produce to detect asteroids in our solar system can be detected all the way across the galaxy. Howard, do you want to do the question answer right away, or we want to keep it at the end?
Oh, let's do it at the end.
Okay. So now the question is that, okay, let's find out how many such civilizations out there. Like if you start looking for radio signals, we start looking for signals that might be coming from ET. What is the chance of detecting? You might have heard about this thing called Drake equation, which is nothing but just a multiplication of several probabilities. So you ask this question that, okay, we have so many stars. How many of those stars will have life on it? How many of those life will eventually evolve to develop intelligent life? How many of them intelligent life will evolve to develop radio communication? And you combine all of these numbers together, you can be a little bit pessimistic or be more optimistic. If you be a pessimistic and you kind of really keep most conservative approximation for this, you might find that life is very, very rare. Maybe there is life in one galaxy, but maybe one life in like one intelligent life per 100 galaxy. Maybe it's that rare. Or maybe it's quite common. Maybe there are 100,000 life in our galaxy itself. If that is the case, for example, if life is rare, that means we are quite unique in our galaxy. So we should look at other galaxies. We should look at all our nearby galaxies, because there is no reason that life will exist just in our galaxy. There could be, maybe the life exists in other galaxies, not just in our galaxy. But let's say we be more optimistic. Life is quite common, or intelligent life is quite common, or type of life you want to search is quite common. So there must be another intelligent life just within the next 1 million star closer to us. So if we search closest 1 million star, we should be able to answer the question whether life is such common or not. And that is the reason we have no way of kind of knowing this, because this is just theory. And as Carl Sagan has quoted, the only significant test of existence of extraterrestrial intelligence is an experimental one. So you need to do an experiment. You need to design an experiment, and then you need to do it. So that's what we've been doing. I'm part of this program called Breakthrough Initiative, which was launched in 2015. Our current sponsor is Yuri Milner. And it was announced at the Royal Society London. So we've been operating for past 5 years. So I tell you a little bit about our program. Our program is called Breakthrough Listen. Breakthrough Listen has these several target goals. So as I mentioned earlier, we don't know how common life is. So consider, let's say consider an optimistic scenario. The life is pretty common. In that case, we should find life in next one nearby star. And that's what we are doing. We are going to look at 1 million nearby stars. Maybe life is rare, somewhere between the optimistic and pessimistic number. Maybe there are a few thousand of them, but they are further away in the galaxy. So we are looking randomly. We are looking actually toward the entire galactic plane. We are looking our entire galaxy. Maybe you take this question and be more pessimistic and say that the life is extremely rare. Maybe there is life maybe in one galaxy per 100 galaxies, in one galaxy out of hundreds of them. So we should look at our nearby galaxies as well. Maybe there is another galaxy somewhere out there which has another intelligent life just like us, and maybe we'll be able to find them. So we have these 3 different set of goals that we want to achieve. Obviously, for covering these 3 different types of target, our observation also needs to be similar. So let me just briefly explain what are we actually looking at. So let's say this is our galaxy. Somewhere in some corner of our galaxy, life suddenly starts, and then that life actually starts emitting radio waves. So you can see this bubble expanding. That bubble, you can assume the radio waves being produced by the life on that system for a very small amount of time. This time is quite important because maybe we are not going to exist here on this planet forever. So let's say if there is life on some planet, it develops intelligence after a while, it develops technology, and then it suddenly starts emitting radio waves. But due to some unforeseen incident, we suddenly perish. Life no longer exists, and there is no longer radio wave. But the shell of radio waves that we broadcasted for that small amount of time still travels. They are still traveling throughout the galaxy, even if the source itself no longer exists. So we here sitting on Earth, producing these radio waves, if such radio waves encounters us, if they passes through Earth, we can use the radio antennas that are already existing to capture this signal. So that's the basic premise of what we are trying to do. We don't know how common life is, but we hope that there are at least few intelligent life spread out within the galaxy, and their radio wave must be passing through us at this very moment. So we use radio waves, we basically use radio antennas to look at these individual stars, look at the galaxy and all lots of targets. And obviously, this is a massive task. Like we are looking at 1 million stars. This is such a huge number of targets. You can never be able to do this within single telescope. So we have lots of telescopes that we are currently operated. But primarily we work with this telescope called Green Bank Telescope, which is in West Virginia here in the US, and Parkes Telescope, which is in Australia. Both of them are some of the most biggest radio telescope in the world. To give an example, this is the Green Bank Telescope, and you can see the size of a truck right next to it. And on the next right picture, you can see a typical sort of human size compared to the size of the dish. It's actually 100 meters in diameter. So it's massive in size. It's like as big as 2 football fields. And it can cover the entire sort of radio spectrum, as I showed you in a few slides earlier, that's accessible to us sitting at the ground. So we have a very limited radio window by which the radio signal can come through the Earth's atmosphere and reach the ground. And we think using the GBT, we can actually cover the entire radio spectrum. So how do we look for signs of intelligence? So basically what we do is that we point the radio telescope towards a star and we see if we find something interesting. Let's say you find something interesting. Then what we do is that we look away from the star and we see whether the same signal exists or not. Why do we need to do that? The reason is that the radio waves that we are trying to receive or trying to kind of capture are in some way similar to radio waves that we generate by our own technology. So that's our biggest challenge. Like the type of technology we are trying to find already exists on Earth. So that interference with our observation. So we need to find a way by which we can distinguish what's being produced by our own technology and what's actually coming from the sky. So how do we do that? We point the telescope in one direction and we see that if the signal is coming from that part of the sky. So this is, like, for example, like a cartoon version of showing you that if you look at the star, you see a signal, and then you look away from the star, and if the signal goes away, that's a good indication. That means that that signal was actually coming from the star. And we do this 3 times. So we do on, off, on, off, on, off. And every time, if the signal exists only on the source and goes away when we look away from the source, that's a good indication that the source is actually coming from that particular point in the sky. There are modern day radio telescopes that's already operational and we are using it, which actually doesn't even need to be where we don't even need to do this on and off, because they can simultaneously look at multiple parts of the sky. So we can look at a star, multiple star in fact, and we can compare what's coming from there, because we don't expect multiple ETs to transmit the similar signal. So we can say that whatever we are receiving, which is same across this multiple position in the sky, must be some kind of interference. But if you see a signal which is only coming from just one part of the sky, that must be signal from ET. But there are other challenges. For example, this is the crowded field. So this is every point here you see are all satellites. They are a big issue to us. So when we look at the stars, there are satellites which are fixed in the sky, but there are also satellites which are moving. And sometimes they pass through your beam when you're observing, and that can introduce signals that we don't want. And that kind of gets pretty hard to really get rid of them. And sometimes we really have to kind of work hard in order to know what we have detected is actually coming from sky or whether we have detected some satellites. So there are lots of such challenges, but fortunately in this modern era, we have a full help of artificial intelligence or machine learning or deep learning, however you want to call it. You can train a classifier, you can train a machine learning classifier to identify things which it has seen earlier. Like for example, signal from satellites. There is a huge amount of various database of classes of signal that typically comes from satellite. A machine can be trained. So we are in the process of kind of doing that. And hopefully that will allow us to kind of, eliminate many of these signals coming from known sources, such as satellites. But finally, no ET so far, unfortunately. Even with the searching for 5 years or 6 years we have been since we launched, we haven't really found ET. But still, we have maybe scratched the surface. Because if we talk about how many number of stars we have searched, it's a very small portion of our galaxy. So what I'm showing you here on the right side is a zoom plot of our own. Let's say this is the Milky Way. Obviously, we haven't seen Milky Way from the top, but it's an artist's impression. And Earth is sitting at the center. The green region you see, you can say that's roughly the region we have searched for life. not so big. So obviously we haven't searched a lot. If you look at the total amount of area that we need to search, you can say that if you compare that to to like Pacific Ocean, maybe we have searched like a size of a glass of water. So there is a whole lot of parameter, whole lot of sky to search, and we are all actively kind of engaging in that. If you want to help us, there is already a lot of tools available online. So please go to our website called Breakthrough SETI.berkeley.edu. Listen. You can download the data. We have tools publicly available. You can download the tools that we use to look for ET, and you can do your own search. You can write your own tools. In fact, there was a high school student who a few years ago who worked with Howard actually. He found some of very interesting signal. Although he didn't use radio data, he used optical data, but basically it was all part of the Breakthrough Listen program. And he found some very interesting laser line signal, which obviously it didn't really come out from ET, but it was an interesting project. And it actually, we were able to kind of write a paper together. So it's a quite nice way of public engagement. So we have all of our data we have collected so far. All of them are public. All the tools that we have developed, all the way that we use is also public. So anybody is in the community is interested in looking for ET with us, they are free to do that. And I'll end my slide with this. If you want to have a take-home message, is very straightforward. Like, we know we are not, the Earth is not unique. If you look at the sky, there are so many planets out there. Every star you see in night sky have planet. So planets are not really rare; they are everywhere. Probably life, we don't know yet, but so far what we have seen from Earth, life, once it kind of starts, it can very easily adapt to no matter what environment you throw it in. So life, once is there, it can survive. It finds a way to reach to a stage of an advanced species. How do you go and find them? So we are currently in the process. We think that radio waves or optical waves are the ways, or electromagnetic waves are the ways to basically search for them. And hopefully artificial intelligence, which is we are using right now, will able to help us go through that. So I'll end it here, and I'll take any questions you have. Thank you so much for your attention.
That's wonderful, Vishal. Thank you so much. That was a great overview, not just of Breakthrough Listen, but of SETI in general. I'll curate the questions for us here, and maybe I can help you out with a couple of them as well. So the first one, it looks like Sunday may be ready to answer this. And the question is, what's the most significant biosignature in an atmosphere? Is it O3 or methane? Sunday, did you want to take this question?
Oh, okay. Well, when you talk about the most important, you first of all consider the habitable zone, which is the exact temperature, not too hot or too cold. And you can consider the thermodynamic equilibrium and trying to check whether how the elements have been changing with time, and how do they change in a way that fits maybe biospheres or micro bacteria there. So when you talk about like methane, is there any UV or infrared? Is there any photochemistry happening, or what is destroying the chemicals there? So we have to consider the chemical, though sometimes scientists consider thermodynamic as the maybe most preferred somehow after habitable zone. Then you can consider whether there is covalent bonding there, then whether there is a cloud of water molecule, how will it dry? But those are the little things they consider. But just know that all habitable zones don't mean they have micro bacteria there, because they are just there. We have many habitable zones in our own solar system, but they may not have life. So we look at the atmosphere and what it contains, and what is the thermodynamic equilibrium saying, what is the covalent bonding, is there any water cloud or molecule, and some other things. Thank you.
Yeah, thanks for that. And I'll just add to what Sunday said, just by saying that oftentimes it's not even a single biosignature, but maybe combinations are becoming more popular in terms of proof positive of a biosignature. So cool. Thanks for that. All right, next one's for you, Vishal. What's the answer to the Fermi problem as adopted by most professionals. Fermi paradox.
Yeah. So I guess as of now, there are obviously several explanations for Fermi paradox. In a professional setting, the answer is that we don't know, right? We are only thing what we could do is design an experiment in order to kind of really see, to basically see what are the ways by which we can answer it. And one of the ways we think that we can answer this question is by actually doing the observation. So like, for example, what we are doing within the Breakthrough Listen group is that if we think that we are unique and like life is kind of rare, as I mentioned earlier, right? We shouldn't be finding life in within like next million years. Sorry, next million stars to us. Maybe we'll find life in other galaxies. If that's the case, that is certainly going to explain the Fermi paradox, that why aliens are not here, because it's quite rare. But let's say we do find life in our next million stars in our neighborhood. That again begs the question, maybe life or intelligent life is common, but space travel is not common. So just the reason that we don't see aliens right outside our window doesn't necessarily mean that they don't exist. Like they could be out there, but it's just that the space travel is so difficult that they'd happen to just not choose to kind of travel and conquer the galaxy. They try to kind of reside in their place where they are. Maybe they are traveling, but not, at least not in our neighborhood. So there are a couple of explanations like that, but obviously the main thing is do an experiment hypothesis. That's what we are trying to do.
Yeah, well said. And I'll just emphasize by saying that, you know, we don't see the Fermi paradox as something that makes SETI prohibitive. We're not worried about that so much. All right, here's one about pulsars, Vishal. It says, although main sequence stars don't, radio waves are also emitted by pulsars, and these are emitted in huge amounts. So is it possible that we can mistake a pulsar for intelligent life?
They did. The very first pulsar, when the very first pulsar was detected, nobody knew pulsars exist. And when they detected these very periodic signal coming from the sky, they obviously thought that what are the nature of processes which could give rise to such a periodic signals, because they knew about quasars at that time. Quasars used to scintillate, but those scintillations used to be quite random. But you never really see something that was so periodic. So obviously when the pulsar were discovered. So now we know pulsars exist. Pulsars have very peculiar nature. So we have no way of like confusing things that we are trying to look for ET with pulsar. So unless ET is deliberately trying to transmit a signal which looks like a pulsar, we have no way of distinguishing it. But pulsars have very particular features. They have signals which are very broadband. The signal from pulsars don't really focus on just one frequency. They actually arrive at all the frequencies. While in SETI, what we are trying to do is that if ET is smart, they try to send a signal which is only concentrated in a very small part of the frequency. And that nature doesn't produce. Let's say you put all your energy into like only few hertz. No natural sources, as of we know right now, can produce a signal which is only few hertz wide. So if you see a signal like that, that's a very good indication that it's not been produced by nature processes. Some kind of artificial process must have produced it, because we do that already. Like all of the signal that we broadcast, we send a signal called carrier signal, which is only like a few hertz wide. So we do that very effectively, which means that if you detect something like that from sky, that's a very well indication that it's not produced by any kind of nature process. So I guess that's that way we can distinguish what's natural and what's non-natural.
Yeah, well said. I'm going to take the next couple, which is how can we contribute, and can you do it from the undergraduate level? I'm putting a link in the chat here to the study.berkeley.edu page /internships. And this has some information about formal and informal research you can do. And of course, all of our data is open to the public, and we have open to the public resources on GitHub. And so you can access some of that there as well. So then there's a question about looking at only habitable zones. And I can just mention real quickly. So the great thing about radio SETI is that you observe a system or a beam that's so large that you encompass any planets that would be in the system. And the great thing about what we know about habitable zones is it motivates our search, because if there are so many planets, as we've detected from Kepler, that suggest that planets in the habitable zones are common, we don't need to be so discriminatory when we look at consider which stars we're going to observe.
Yeah.
And go ahead, Vishal.
Now, I'll just add to, I mean, Howard has actually done a great work on this area. Howard has created a list of targets which actually covers all different types of stars, irrespective that star has planets or not. So we are in some way agnostic. We don't really care if any particular star that we are looking has planet or not, because we know that planets are everywhere. So irrespective whether you have found the planet at this point or not, it doesn't really matter. So as long as you are doing this sensitive survey of nearby system, that's the only thing that we currently focus on. So we try to look for all different types of stars. And Howard has actually created a nice list of stars that we use within the LISTEN program.
Thanks, Vishal. There's one more question I'm going to ask you to take on the chat. And then there's also a question about internships from India. So if you could post the brand newly available opportunity for Indian students in the chat, that would be appreciated as well.
Yes, sure. I can just mention on the call as well. So we are collaborating. I'm from India, by the way. You might have noticed by my accent. But I did my PhD in India, and I'm quite interested in getting SETI started in India. So we are collaborating with a university called Amity University in Mumbai, which is already doing work in astrobiology. So we are currently hiring students for 6 months to do research on SETI. So I'll post a link here. So feel free to kind of reach out and apply.
Thanks again, Vishal. We're going to transition to the next part of the talk. And so people can continue to ask questions during the call today and follow up with Vishal. Thanks again, Vishal. All right, let me just put this transition slide up here for one moment. And then I'll show you this quick look at the Breakthrough Listen website that shows the internships. And so you can look at some of our information here at that link I posted in the chat. And next, I'm going to talk about our final projects. So we have 2 more weeks in terms of days. This is going to be our last formal meeting, and our meetings next week will take place on individual levels. We're going to be organizing individual meetings through Piazza, and so you have a chance to work on your ideas for your final projects and even get feedback on your drafts. And so this is a link here on the Intro to Astro 2021 page. At the bottom here, it's not in one of the weeks, but it's here in the final projects link here. And you can read this over on your own, but we'll go through it briefly here as well. And the idea behind these projects is that it gives you an opportunity to come up with a creative idea on your own and then get feedback from our expert mentors on some of those ideas. And this can be kind of hard feedback to get because people are hard to access at universities and whatnot. So we're hoping that you really take advantage of this and do interact with our mentors on this regard. And so we'd like you to start by coming up with an idea. And so the different idea topics you can come up with include, but are not limited to, things like exoplanet atmospheres, formation of exoplanets, dynamics. We heard a little bit about astrobiology and SETI today, but in earlier weeks we heard about radial velocities and transits, which are all open to study. And there's some other ideas down a little bit further here. The idea is that you start by getting sort of a few sentences of a description about what you want to do. We want you to have that by just in the next couple of days. So do some brainstorming, think about what you might want to be interested in exploring. And next, we want you to use ADS, Astrophysics Data Service, which we talked about in one of the early weeks of this course. We want you to search for it using these keywords that you've come up with in your brainstorm. And so that you have sort of 3 to 5 sentence description of what you want to do by the end of the week. We want you to then put that into an outline form. And all of these steps you're free to engage with and seek feedback about. Once you have an outline, we want you to turn that into something that's at least 2 pages, preferably a little bit more, of double-spaced 12-point font. These are just to help you get an idea of how much content we want you to create. You're welcome to include figures and graphics as well. Since this is more of a proposal of an idea of what we want you to do in the future and not so much something that you've actually carried out, it's okay to use graphics from other papers as long as you say in your proposal that where they came from. So look through this. There are some more links in, if you go to the week 7 SETI link here, there are, apologies, it's in week 8. Let's go to week 8 really quick. Final projects. There is a couple links here that you have a chance to look at, and I'll make sure that those are available on Piazza. And the idea is that there's some links that will help you, give you some examples of what you want to do. And these are examples from the National Science Foundation fellowships that are proposed for graduate students. And so these are real examples of things that people are doing. These are real programs that people apply to for this type of thing. And, this is just an opportunity for you to improve your website. So you can, you've made your websites already in this class. You've made your CVs, which you're going to put in your websites, and we're still open to review those if you post those onto Piazza. And then finally, we'll give you feedback on those proposals. You put those on your website, and then when people go look for you professionally, they can see all the work that you've done. So please post your questions, your summaries, your outlines on Piazza for feedback. And with that, I will hand it off for our final discussion of the direct imaging paper to Priya. Are you ready, Priya?
Yeah, thanks, Howard.
All yours.
Yeah. Let's share my screen. Yeah, so before I start on the paper, I wanted to just do a little bit of a background. And so I'll start from this. So this is the paper that we are going to discuss, which is on direct imaging of exoplanets in the era of extremely large telescopes. And let's see. So all of you all are already familiar with all the different kinds of methods which are actually used to detect exoplanets. And obviously, like you can see the direct imaging method, which is blue, you almost can't even see it on this plot. It's very, very this thing. And why is that? Why is it that you have it, it's such a small contribution? And that's basically because of the problems in exoplanet detection. Essentially, the planet is extremely faint compared to the parent star. And therefore, so for example, if you have a star like the sun, it's about 1 billion times as bright as any of the planets orbiting around it. And therefore, it's what happens is that the light from the parent star, it causes the glare that washes out the planet, and therefore you cannot even see it, right? Like you don't see stars in the day. And therefore there are various indirect methods used to detect extrasolar planets, which we've been talking about. Exoplanet imaging is therefore something which is coming up. It was not the popular method to do it because of these basic problems. And like I said, because it's very difficult to resolve them. And it's easier to, there's also an observational bias when you observe it, that it's easier to obtain images when the star system is relatively near to the sun, and when it's specifically large, and Jupiter-like planets, they're easier to detect. And it's obviously, these are colder objects, so they are very good to detect in the infrared, where the planet is brighter than at visible wavelengths. And often coronagraphs are used to actually block the light from the star, where so then you can actually see the planet. And it therefore requires a lot of this thing. There are some specialized techniques where you specifically look for the light from the planet in a specific wavelength. For example, in the H-alpha wavelength, where you expect to get more emission coming from this thing. Interesting to note that even X-ray emission from planets is also interesting. People are even using Chandra data to find exoplanets, and there's a whole range of methods used. Now, the different observing methods is, for example, the imaging method. You have medium and high resolution spectroscopy, which is used for it. And you could also have what is called an integral felt spectrograph. That is, you combine coronagraphy with that and polarimetry. So there are various kind of combinations that people try out to actually detect these objects. So here, for example, you can see this is an image of direct image of exoplanets for the star, this thing, where you can see it's through a coronagraph, you actually cut off the light from the star, and that's when you can actually see the planets over here. This is from the Hale telescope. There's another popular image over here, which is a Beta Pictoris. This is with a 3.6 meter telescope. This is an old image, but over here where you can actually see the debris disk and various features. Now, the paper that we are talking about is about the extremely large telescopes, which are going to come up in the next decade. And this is the GMT. This is the TMT, of which India is also a partner. And this is the EELT, the European Extremely Large Telescope. So these are the three basic telescopes which are going to come out probably in the end of this decade. And the paper is basically targeted at exoplanet imaging, specifically with these telescopes. Now, these telescopes here, you have them, and here's a list of all the kind of instruments that would be available on these telescopes. These are what are called the first light instruments, which are being planned. And these are ones which would be actually playing a role. Now, if we actually see, this is part of the paper, but I'll get back to it. It basically shows you a timeline of the different kind of techniques, the missions and instruments used to detect exoplanets. So you have here the ground-based ones, some of them which I showed you the images of. And then this paper is from 2018. And then you have ALMA, which is already operational. This is a millimeter wave telescope. And then you have the radio, the square kilometer array. And then you have a bunch of these ones, which are ground-based, extremely large telescopes, which come in later on, right? And this is also part of the telescope, so after part of the paper, so I'll talk about it when we come to the paper. The instruments, and these are the spectral resolution, the wavelengths in which they operate. This is for the ELT, this is for the GMT, and this one is for the TMT. So I'll now go to the paper, and we'll get on to this. Yeah. So this is the paper which we are actually discussing today, which, like I told you, was about direct imaging of exoplanets. This is the GMT. And the present era, right, is the era which is basically still of large-scale systematic surveys, which are actually being used to get a good consensus of the exoplanetary systems within 200 parsecs from the sun. So you'll have already you've already seen the Gaia data, which we spoke about, as well as, for example, the Kepler data. These are basically data sets which are used to characterize the exoplanetary systems within the neighborhood of the sun. And obviously, the next step would be that once you have this consensus of the exoplanets in the neighborhood of the sun, that's when these extremely large telescopes will point at individual objects and actually try to look at their individual situations. So the key science cases are basically for looking for the initial conditions of planetary formation, architecture of planetary systems, and the physics and atmospheres of giant telluric planets. So that's the basic job that these extremely large telescopes are going to do, where you're going to do pointed observations at these objects, which have been well studied using various surveys, right? So, like I mentioned earlier, this will basically give us an understanding of the several mechanisms used to form giant planets, because this is when you're going to actually see this at a very, with very good resolution, the physics of accretion and their formation, the physical properties of young Jupiters, and the impact of dynamical evolution. So the idea is that you would be actually looking at planets orbiting at about 5 to 10 astronomical units. One astronomical unit is 150 million kilometers, which is the distance between the Earth and the Sun. And this is, slightly larger distance. And we'd be actually characterizing these planets, right, with this kind of systems. So I'd already shown you this plot, and this basically shows you a timeline of the various missions that have been conducted, which actually are looking for this. So we are actually in this era, the space era, in which we are actually using, we've already used Spitzer, Herschel, Kepler, Caro, Gaia, TESS, and soon JWST. These will all, characterize these systems. And then we'd actually go into this other phase where we'd be individually checking out on this. So, and like I mentioned, there's square kilometer array and there's ALMA. So ALMA is already operational, and you're going into a spectral resolution of about 0.1 arc seconds. And then you'd actually further go on with square kilometer array. The Gaia data release 4, at present, what you saw in the Gaia data release, that is the, what is on is called the EDR3, the early data release 3. But even the DR3 will not have the data required for exoplanets. For exoplanets, the proper data will be available in the data release 4. And that's when you will get you'll get proper light curves for stars. And you will actually, for stars closer than 200 parsecs, and you'll be able to characterize them. TESS we've already spoken about, we won't be going on there. And then you'd also have GEOPS, which will come in and also be used for this. So, but we expect that within the next 10 years, this is 2018, within the next 10 years, we'd actually have a good complete consensus of all the exoplanetary systems within 100 to 200 parsecs of the sun, right? Once we have this. The characterization will intensify with JWST, which is soon going to be launched. hopefully in this year or the next year. And that's when we'd have these things. So these are the basic instruments which are going to be there on these extremely large telescopes. The IMG refers to the imaging mode. This is the medium resolution spectroscopy. This is the integral field. So in integral field, what happens is at the telescope, you have various feeds or various points where you're specifically taking the light from those points, and you can analyze those, do spectroscopy of those, and get data for that. And these are the instruments which are being planned for the telescopes, right? So like I mentioned, now that the era is coming in of the extremely large telescopes, that's when we are going to get really unique spatial resolution for these objects, right? And these 3 ELT projects, they are essentially all 30 to 40 meter class telescopes. And what's interesting is, I think I showed you an image of them. The GMT is basically made up of only 7 segments of individual 8.4 diameter telescopes. TMT is made up of 492 segments of 1.4 meter, segments over there. And these are ELTs made up of 800 segments. Now, all these instruments have very specialized instrumentation, which is called, there's something called active optics and adaptive optics, with which they can actually give you very good resolution on the Earth. We won't go into those details of that, but these are the AO systems which are there on it, which actually ensure that even if you have bad seeing through the atmosphere, you will still be able to get very good resolution using these telescopes. And basically, this is the different resolutions. You can see at what distance, when you come out from the host star, would you be able to see different structure in the planet forming regions around these young stars, right? And so what is expected is that you would actually get an astrometric precision of about 100 million micro arc seconds, right? Will be achieved for stars at a distance of 100 parsecs. You'll be able to see the properties of the inner circumstellar disks, which includes asymmetries. Actually, I should have put a picture of even ALMA. ALMA already shows you very beautiful images of protoplanetary disks, where you can actually see structure in the protoplanetary disks, which include lumps and gaps and various regions where planets are being formed, etc. And here you could also get what are called velocity maps. So if you have good enough this is a simulated CO12 emission from a protoplanetary disk. So here you have a protoplanetary disk, and this is using the instrument METIS. And you can actually, if you have good enough resolution, you can actually get a velocity map. So by a velocity map, you mean to say here you are going in for redshifted and blue shifted light. So you can actually see the motion of the protoplanetary disk, which is over here. And you can actually, the resolution you'd get is a resolution of 100,000, which is approximately 3 kilometers per second, which is what is expected with the ELT, right? And so once we have direct spectral imaging of planetary regions with the ELTs, one would be able to observe them with this amount of high spatial resolution. Now, spectral imaging basically means that you look at the spectrum of you look at the light in particular wavelengths. Like, for example, this is in carbon monoxide 12, but you may look for it in other wavelengths, looking for specific structures, right? And what is expected is that these are essentially in optical and infrared emissions. But if it is complemented with ALMA, ALMA is in the millimeter, SK is in the radio, you would be able to characterize the cold outer dust as well as the different components. You are all aware that you are going to observe different components in different wavelengths, and therefore you can very well build up a good enough structure of the of the different the features on the protoplanetary disk, right? And it will also give you an idea of the organic content of the planet forming regions, which include methane and various other chemistry which is present in the thing. So like I mentioned with the first light instruments, these are the first light instruments for these extremely large telescopes. A combination of high angular resolution and moderate high contrast will actually be able to help us to detect fine gaseous and dusty structures, which include the biosignatures that were being spoken about, and like I said, this is essentially going to be in the visible and the mid-infrared. And once we have the synergy of these ELTs with the other, the transit measuring instruments, etc., we would have a very good understanding of the frequency, multiplicity, distribution of mass and orbital parameters, as well as stellar properties of these exoplanetary systems, right? So here, if you can see this plot over here, this is what is expected with Gaia. Here you have what is expected with JWST. Gaia is going to give you these kind of distances from the star, which you can see over here. This is what you have with Cheops, TESS, Plato, etc. And then once you come in with these instruments, these are the ones which we are going to get from the extremely large telescopes, we'd have a good idea of these regions of the protoplanetary disks around young stars. And in principle, already the era of characterization of exoplanets has already started. I showed you some of those images which are already available using VLT, the high spectral resolution using VLT, as well as various other instruments. We already do have some very good images available, but obviously the big boom will come when we have these extremely large telescopes with all their amazing instruments, and we'd have a very good characterization of exo-Earths, and possibly the first probable discovery of exolife. But this is something which is obviously much for the future. So thanks. I'll stop with this. You can have a look at the paper. It has a lot more detail. I just tried to give you a broad overview.
Priya, thanks so much. And expect to see some proposals in the next few weeks that have direct imaging as part of their proposal. That'll be kind of fun to use this paper as one of your 3 papers you'll need to have as references. So thanks again. With that, I think we're gonna wrap up here. So big thanks to Priya, big thanks to Vishal today for leading the discussions. I'll send out another email with more information about the final projects, and we hope to see more chatter on Piazza about what's been going on, and yeah, more details to come. Thanks very much, everybody. We'll talk to everyone this week and next week. Bye.